Okay, so I'm going to make a start. So today's lecture is a continuation of what we were talking about on Monday to do with looking at for STL containers. And so we're going to recap on what we went through quickly on Monday, and then we're going to look at a couple of containers that we didn't get a chance to look at. And then we're going to look at iterators and how iterators work and glue the containers together along with STL algorithms. So on Monday, we talked about the idea of the STL library having containers, iterators, and algorithms. And iterators being the glue between a variety of containers. And so the idea with these things being generic types and being templated types is that we can have a number of algorithms, a number of containers, a number of iterators, and they work across all of them without needing to be strictly container dependent. Okay? So we mentioned that algorithms manipulate data, but they don't actually know about how the container underneath works. We mentioned that containers store data, but for algorithms that work on them, they don't know about them. And iterators being the glue that connects the two of them, and so they interact through the iterators. But each container contains its own iterator type. And an iterator itself is a type that helps work with a container. A container is also a type. And so in C++, in the STL, there's this set of containers here. There's sequence containers, there's adapters, there's associative containers, and there's unordered associative containers. And so we went through the sequence containers, we very briefly mentioned the adapters, and today we're going to be looking at the associative containers. We spent quite a bit of time looking at vector. And talking about a vector is basically a dynamic array. And so it has both a size and a capacity. The size is the number of elements that's contained within it. The capacity being the amount of stuff it can store before it automatically increases in size. And we talked about the constructors and all that for vector. Then we also very quickly mentioned a list. And by default, a list is a doubly linked list. And in fact, there's no methods for random access in a list. You can either get for front or end of the list. Okay. But there is methods for fast merging and changing of lists. Okay, and some code there and some code on the lecture slides on Monday. We also mentioned the idea of a forward list, and a forward list is a singularly linked list that has less memory, but it has a much slimmer interface. So there's no minus iterator, you can't go backwards for it. There's no dot size operation on a forward list. We also very quickly mentioned a DQ, a double-ended queue. And we also mentioned for C++ 11 style array. And for C++ 11 style array, even though the size is fixed at compile time, you can then end up using it with STL algorithms, and it provides iterators, it knows its size, it provides a number of member functions that a standard C-style array doesn't include. And then we very briefly mentioned stacks, queues, and priority queues. They're built on top of these containers, and you're encouraged to build your own types of containers on top of these base containers. Okay, so that's what we've been over on the second half of Monday lecture. And those are all sequence-based containers. What I mean by sequence-based is you have some data you put in, some values you put into these containers, and they're often indexed. So you can go to a certain index on them. So regardless of if you've got an array or a linked list or something like that, there's some sort of order or some sort of sequence to ordering that makes sense, just as 1, 2, 3, etc. Today we're going to be looking at associative containers. And so associative containers, you've probably seen them already in previous courses. They're containers that have key value pairs. So there's no strict ordering over them the same as you have an index on an array. Okay? They have a value type, which is the same as a sequential container. The value type is the thing that you're storing. So for elements accessed by a key, and a key is often a second data type. The elements may be ordered or unordered. They're often unordered, and they're often unordered by their key values. Okay. By default, we use the less than operator to compare keys in an associative container. So when you're building your own containers later on, your own classes, you often need to override or provide implementation of the less than operator so that you can compare different keys in an associative container. Okay, so what containers do we have? If we go back a couple of slides, we had associative containers being a set, a map, a multi-set, and a multi-map. Now, can someone very quickly tell me what a set is? It's a collection that doesn't contain duplicates. Does it have an order? A set is also unordered. What is a map? It's a set of key value pairs. What's also a common different name for map? A dictionary. Okay, dictionary. So if you're coming from Python or something like that, you often have the idea of a dictionary. A dictionary and a map are very similar. They're a set of keys and a set of values, and there's a mapping between the keys to the values. Okay, so we jump back up to here. Let's look at a set. So we said that an associative container has keys and values, but we also say a set is an associative container, and that's because for a set, the value type and the key type are the same. So both the keys and the values are the same piece of data. So looking up at the code, up on the screen on the left-hand side, we can have a set of ints, and we can push the number 1 in, we can push the number 2 in, but we can't push the number 1 in the second time, because we can't have duplicates. Okay, so you might get a compile, or you might get a runtime error at that point. On line 6 and 7, let's create a new set. And so we're creating a set of something that's called sales data. So we've created our own custom data type called sales data, and we create a set of those things, and we go to put a sales data object into the set. But let's say the sales data object hasn't had the less than operator defined for it. Okay? We won't be able to do this because the less than operator is not defined. Okay? Now we're going to look at classes next week. We're going to look at operator overloading for week following. Okay, so you don't strictly have to understand what's going on here in terms of the sales data class, but you need to understand the idea of a set containing things that can't be duplicates, and the idea that anything you put into that, any type that that set is holding, okay, needs to have the less than operator defined because it does the comparison on that. If you're coming from Java, this is a very similar idea. So often containers need to have the .equals method defined on them. Okay, so instead of equality here, we're using the less than operator. But it's the same sort of idea. This comparison operator needs to be defined. Okay, we can then talk about maps. And a map is a collection of pairs. Okay, so key value pairs. And so for a map, we have a key type and a value type. They can be different types, okay? And that gets formed into a pair of keys and values. And then you have a set of keys and a set of values. Okay, everyone should hopefully already know this. So we have an example here of how this works. And I actually will bring this up in code as well, up here. Okay, so we've got map.cpp. What this code does is it creates a map of strings to doubles. It means that strings are keys and doubles are the value type. Okay. We then create this thing called a standard pair. And the standard pair is the pair of the string to the double. So we create 3 pairs of data. Bat has the value 14.75, cat has the value 10.157, and dog has the value 43.5. Then we insert those pairs into our map. Okay. And then what we can do is we can use a for loop with auto data type and iterators to iterate over that collection. Okay, so even though we said it's unordered, we can still iterate over that collection. Okay, and we can then access through that collection that auto. So it's MIT data type here. This MIT variable gets back a pair. And so with a pair, we have the first element and the second element in a pair. Okay, so the key and the value. And so we can print out the key and the value. Now, even though I said we can iterate over this, and it's unordered, what that means is this iteration order is not guaranteed to be the same ordering as which we inserted the stuff on lines 10 to 12 at that point. So even though we inserted bat, cat, and dog in that order, there's no guarantee that when we print this out, it is going to be in the same order. It might be, it might not. Let's take a look. So make map. Okay, so we compiled it. And I run it. Okay, so in this case, it did come out in the same order. Okay, but there's no guarantee of that. What I could do is I could insert some more data into there. So again, there's no guarantee that this is going to completely work all the time. Oops, what's going on here? Okay, so I'll insert some more stuff. So use 4, 5, and 6. And that can be a big dog, and a little dog, and a tiny dog. And so he can have that value, and he can have that value, and he can be this value here. Okay, and we fix up these inserts. Okay, and we recompile that, and we run that again. Okay. Okay, so here we go. So if we look at, oops, don't do that. Okay, you can't really quite see it all on the screen at the same time, but if we look at insertion order, we inserted 6 things. We inserted a bat, a cat, a dog, a big dog, a little dog, and a teeny dog in that order. If that had been a sequential container, such as an array or list or a linked list or a vector or something like that, when we did the for loop over that, it would have come out in the same order. Because this is not a sequential container, when we iterate over it, we get a bat that is the same, but then we inserted a cat second, we don't get the cat second. We get a big dog as the second element. We then get the cat, the dog, the little dog, and the teeny dog. So there's no ordering in the same way in which there is over a sequential container. Okay. For many of you guys, this should be revision. If not, just understand that this ordering is different. Yep.
Is it a coincidence that that's alphabetical?
I have no idea, to tell you the truth. I have absolutely no idea if that's a coincidence, if that is alphabetical. It may be, it may not be. Okay? So something might be going on there underneath. Remember, we had to define the lesson operator. So it possibly is that on standard string, that lesson operator is being used to give it some sort of order. Okay, but that's not guaranteed. That's the point I'm making. It's not guaranteed. But try it for yourself with some different data types, maybe some instants and doubles, and see if the same thing happens. Okay. Okay. So what we can then do is with a map, if we want to find if something's in the map, we can go and look for it. Now we can use the random access iterator, or random access type overload here, to go see if, so we've got a map of words, if the word bark is in that map. Okay? And so if that's equal to 0, it's not present, because it's giving us some sort of index, even though it don't have indexes the same way. But this is kind of a little weird way of doing it. Okay, so instead what we should be doing is we should be using the find function on the map. Okay, and that returns an iterator pointing to the queried key value pair. Okay, So what we can do is we can say standard map, a map of string to int, get me for iterator type on that map, okay, so it's IT. Iterator is equal to words, so words being our map container, dot find, and then it's finding on the key. Not on the value, it's finding on the key, okay? And then if the iterator is not equal to the end iterator on that container, so if it is equal to the end iterator on that container, that's not found. If it's equal to something other than words.end, then it is found in that container. Okay? So with iterators, let's go back a slide. With iterators, we can iterate from dot beginning or dot begin to dot end. Okay, so dot end is one element after the end of the container. We'll explain this more in a few minutes. Okay. So if the iterator doesn't find it, the iterator gets set to the end of the container. Okay, we clear on that for map. Okay, so there is other associative containers. Okay, so there's multi-set and multi-map. Now, multi-set is actually a bit of an oxymoron because a multi-set allows us to store duplicates. It allows us to store the same key or the key multiple times. Okay, so for a multi-set, that doesn't quite make sense in the definition of what a set is, but C++ allows you to do it. Okay. And then C++11 gives you these ideas of these unordered sets. Okay, so your question before, here's the answer to your question before. This is ordered in some way. Okay, so this is definitely using the lesson to order it. So I'm assuming it's ordering by alphabetical because we're using strings. You can then use an unordered collection to do that. Okay? So there is some sort of ordering, but it's not guaranteed in the same way in which a sequential container is ordered. Okay? Okay, so that's the end of containers. Okay, so we've got the idea of all these different containers. Depending on what problem you're trying to solve, will dictate what one you're going to use. Okay, so you get a problem, you work out what container you can use. Like I pointed out on Monday, the really nice thing about using the STL containers along with the STL algorithms is if halfway through your program you realize that you're using the wrong container. Won't guarantee you always work this way, but you should just be able to go change the data type at the top. So if you want to change from a vector to an array, you should just be able to change where you say vector, change it to array. All the pushbacks and stuff should all keep working. Not always guaranteed, but that's a rough idea that you can do. Okay, so you can swap out the containers very simply because they've all got the same interface on them. Yep.
Isn't a set unordered by definition? So
a set is unordered by definition, so yes, I don't understand why you have that, but Sean.
Sets are actually stored ordered in C++, so are maps, and that's why there's unordered types as well that have been added.
So there you go. So the mathematical definition of a set is unordered, but C++.
The difference between an associative container is that when you insert it, it gets ordered by the less than operator, when a sequential container gets inserted by the order you actually insert things.
So that's the key difference you need to know. Okay? Okay, so let's talk about iterators. So talked about all these containers. Okay? Now let's talk about iterators. So people have probably seen iterators before, again, if you're coming from Java. Could someone give me a rough idea of what an iterator is or what you'd use an iterator for? If I want to iterate over something, what does it mean? Go from beginning to end, okay? So that's how you'd normally use an iterator. You'd think about starting at the start and going to the end, okay? Yeah, so iterators allow us to go over a collection, but it's more than just starting at the start and going to the end. Probably what you've done so far in coding has just been start at the start and go to the end. But as you'll see in the next few slides, there's a number of different iterators and different things that we can do with C++ iterators. Okay? And like I've said a few times, they're the glue between the containers and the generic algorithms available in VSTL. Okay? So here's an iterator for a container. Okay? So A is a container, and it's got n objects ordered in a particular way. And so A.begin points to the first element in that container. a.end points to one position past the last element, whatever that means. In a sequential container, it kind of makes sense. For a associative container, that is a little more abstract, okay? But you've got this a.end, this end iterator, which is pointing to something past the end of the container. Okay? Like I said on Monday, an iterator itself is a data type. Okay? So the iterator is not a collection, and it's not the value stored in the collection, it's its own data type. And so to look at the object that's being pointed to by the iterator, we dereference it, same way as we dereference a pointer. And we can use plus plus and minus minus to go forward or backwards on an iterator, provided that particular iterator has it defined. Okay, so we've seen this loop a few times for, it's probably have auto in front of it, but for first equals a.begin, and first is not equal to the end, move forward on first, and then do something with it. Okay, that's the type of iteration you've probably seen before, in, if not C++, and other programming languages. Okay? Okay, so every iterator itself is non-const. Okay? It makes no sense to have a const iterator in the same way we might have a const value, because if we had a const iterator, we couldn't plus plus or minus minus, we couldn't move the iterator forward or backwards. So when we say we have a const iterator, it doesn't mean exactly the same as what const normally means. It means that what it's pointing to is const. Okay? So we might have a const iterator that allows us to move back or forward along a container, but it means we can't update for things in that container using that iterator. Okay? So say if you're printing something out, you might want to use the const iterator because your code to print something out shouldn't modify the elements in that container. We might want a non-const iterator if we want to update stuff in that container. So imagine that we have a container of some sort of number types, so some sort of ints or doubles or whatever. And for some reason we wanted to normalize them, okay? So we wanted to turn them into a value between 0 and 1. We would use a non-const iterator to do that because we'd get the value at that point and we'd divide it by some arbitrary value to make that normalized. Okay, so the non-const iterator allows us to modify values in a container. A const iterator just allows us to go over the container without modifying the values. Okay, so that should be pretty straightforward. So there's two sets of code on this slide here. Okay, so this is an iterator for a non-const container. There's some pre-C++ code which are just left up there for reference, and there's some C++ 11 code. You should be using the C++ 11 version. And in the C++ 11 version, there's actually, again, two different ways of which you can do this. You can use for auto type, for it to automatically work out this code needs to be non-const. Okay? And this is because, well, can someone tell me what they think this loop is doing? This loop on lines 1 to 5, what's it doing? So we have a vector called x. Okay, it's up the top. Vector x up the top. It's got 10 elements all defaulted to 1. Okay, so it's a vector containing 10 elements. All those elements are value 1. What do people think that down here? Yeah, so it's printing every element, so it's printing 1 10 times. And then every time it prints 1, it's changing that value to 10. Okay, so that's why it's non-const, because it's modifying it. Now, you see how this is .begin here? You can also ask for const iterator to be inferred, okay? Which, instead of .begin, we have .cbegin, .constbegin, and .cend. And so now this printout will work because the printout doesn't modify it, it's fine. But when we try to change the value to 10, we'll get an error because it's const. Okay, so you'll see this when we go to the next slide. Okay, iterators for a const container. You had to ask for a different type up the top, you had to actually ask for a const iterator. Using C++11, which we are using, if we have code like this in the middle, okay, we're not modifying the container at all, that const iterator is automatically inferred using the auto data type. Okay, so auto is very, very powerful, and C++11 allows us to work out these things automatically. Okay? Yep.
Can you go back to the
Previous slide, yep.
does that mean in C++, you don't use the C begin and C end, you also give the constant iterator? Because the next slide, you're not using the C begin function.
Yeah, yeah. Provided there's not a mistake on the slide, that's correct. Okay. Now, note you cannot obtain a non-const iterator from a const container. Does someone understand what that means? That you cannot obtain a non-const iterator from a const container. What does it mean? What do people think that means? Yeah, so say I have a container of const ints. Okay, so it's a const container. It's containing ints that are const. I can't modify those values. I can't get a non-const iterator over that collection because that doesn't make sense. Because that non-const iterator says that I could try and modify those values. Because those values are const in that container, I can't do that. Okay. Now, const ints probably don't make much sense, but you might be using containers with const references in them. Okay. And so if you've got const references, then you'd want a container that does not modify those references. Or the same thing if you had a container of const pointers. Okay? So that's a standard forward iterator we've looked at. If you haven't seen iterators before, you've probably seen something very similar in different programming languages. Let's look at some different types of iterators now. So this is a reverse iterator. Should be quite easy to understand. It does everything backwards. So if we ask for r.begin and r.end, and then we move forward on the reverse iterator, we actually move backwards over our collection. Okay, so reverse iterator just flips the idea of moving along the container, and we move along backwards. Okay, so the first thing points to the first thing points to the last thing, and the last points to the first. And so when we go plus plus on the iterator, we go backwards along our container. Okay? So reverse iterators should be reasonably straightforward. So we have 5 categories of iterators. We have output, input, forward, bidirectional, and random iterators. And hopefully on the next slide, I'm going to come back to the slide, but hopefully on the next slide, no, there it is. Okay, these things are hierarchical. You have either an input iterator or an output iterator. An input iterator is a little bit weirdly named because an input iterator allows you to access the values but not change the values. An output iterator actually allows you to change the values. So input and output are kind of reversed in those namings. A forward iterator allows you to move forward over the collection and change the values as you go, but it doesn't allow you to move backwards. A bidirectional iterator allows you to move forward or backwards and do or change the values across the container. And a random access iterator allows you to go directly to the middle of the container and, again, change or view the values. And so it's sort of a hierarchy there, and there's more power the lower you go down that hierarchy. Now if I jump back to that slide there, these are the sort of things you can do with iterator. If you want to read data, you can't read data from an output iterator. You can read it from an input, a forward, a bidirectional, and a random. If you want to access the data, again, you can't access it from an output iterator, but you can from an input, a forward, a bidirectional, and a random. If you want to write data, so change the value somewhere. You can do that on output iterator, but you can't do it on input, and you can do it on all the rest. Iteration, moving forward or backwards along your container. Output, input, and forward, you can move forward only. You can only move one way through your container. Bidirectional, you can use minus minus to go back. And random, you can do things like addition and subtraction of iterator values, plus equals and minus equal of values to skip forward and backwards along your container. You also have a comparison iterator, which allows you to compare values. And different algorithms, so remember we've got our containers, we've got our iterators, we've got our algorithms, and iterators being the glue between them. Different algorithms require different types of iterators for their operations. Okay? So for algorithm find or equals, requires an input iterator. Okay, because it's just working along, looking at the values. Copy. So if we want to copy a container using the copy algorithm, we need an output iterator for it because we need to be able to write values. To replace something, we need a forward iterator. Okay, so these down here are all STL algorithms. If we want to reverse something, we need a bidirectional iterator to move forward or backwards. If we want to sort something, okay, we're going to come back to this point later on today, and this is also going to be a tutorial next week. If we want to sort something, we need a random access iterator. Okay, so standard sort requires a random access iterator. This is why for forward list, for container for forward list, where this doesn't have a random access iterator, you cannot sort a list using standard sort. Okay? Now we'll come back to that in the tutorial next week. Okay? So if we look at the container, here's a mapping of containers to the iterators that they contain. Vector and a double-ended queue both have random access iterators. You can go anywhere throughout them. List is bidirectional. You can go forward backwards because it's a double-ended queue, list. Sorry, doubly linked list is what it is. A forward list is only singly linked, so you can only go forward. A stack, a queue, and a priority queue do not have iterators. Stack, a queue, and a priority queue do not have iterators. You can only access the front of them, okay, because they're adapters. A map, a multi-map, a set, and a multi-set, being them ordered or unordered, okay, they've got bidirectional iterators. Okay, so you can move forward or backwards, but you don't have random access. Okay, and in assignment 3, you'll be asked to build your own iterator for a particular class template that you're going to build. Okay, so later on in this course, you'll be building your own iterator to go over a collection. Okay, so we looked at this slide already. There's a hierarchy that's involved. Okay, so we've got this idea so far, because this is about to get more complex in the next couple of slides. We've got the idea. There's different iterators, and they do different things over different collections. Okay? Okay, so let's look at iterator invalidation. In this code, we have a vector of 5 elements, okay, 5 ints. We then have an iterator to the beginning and an iterator to the end. Okay, so first is pointing to the first element, end is pointing to one past the last element. Now, if we use the algorithm find to find the number 3, okay, so this is what it's doing, it's finding the number 3, and we want to insert the result of that into position 6, okay, doesn't make sense, okay, because there are only 5 elements in this collection. Okay, so that's not going to work. Okay? So the point down bottom here is there's lots of different algorithms available in the standard template library. Okay? Before you use them, you should read the documentation to understand how they work. Okay? Because otherwise you can end up with an invalid iterator. If you've got an invalid iterator, your code's probably going to crash. We can also use different types of iterators to do different types of things. So here's what's called an iStream iterator. This iStream iterator is very similar to what we saw on Monday with reading a file. Okay, but this is a different way of reading a file. We create an input file stream, say data.in, okay? And on Monday we would have just done while that file read it into a value, keep looping until we get to end of file. Okay? We're going to do a similar thing but with iterators today. So we create an iStream, so input stream iterator, begin, okay, and we pass it in that input file stream that we're looking at. We create an end iterator as well, okay, which we're not going to set to any value. It's just called end, okay? We can then do something like this. Print out, begin, so that iterator, dereference that iterator, print out that value plus plus. What do people think that line of code is going to do? Star begin plus plus.
Prints out the value and iterates to the next value.
Yeah, so that prints out, I don't have that code unfortunately in my demos, that code will print out that value and then automatically move to the next value, okay? Because the plus plus is post-increment, it happens after that star begin has happened, okay? Line 6, we're just going to skip that next line of input, and then we can print out preferred value like that, okay? And we can, of course, put that into a loop, so while begin is not equal to end, keep going. Okay, that works fine. So that's an input stream iterator. It's looping over an input stream. The back insert operator, back insert iterator, allows us to insert things at the back of a collection. Okay? So we can do this. We can say, give me an IO stream, give me an input stream, again, give me this file. Okay? Create me these iterators over that file. Okay, this is the same as the previous slide. Create me then a vector with nothing in it, so he's got a vector. Then create me a back insert iterator over that vector. Okay, so a back insert iterator over that vector. And then while begin is not equal to end, so our input iterator is up here, while begin is not equal to end, this back insert iterator which you've got here, dereference that value to the value that's in dot begin. Okay, and so copy all the data from that file into that vector. Okay, so it's a very fast way of reading all the data in that file into a vector. Okay, so there's how many different iterators are in this code? 2? No? How many different iterators in this file? 3? Yep. You have 2 input stream iterators, okay, the begin and the end, and you've got 1 back insert iterator. So this back insert iterator knows where the back of that vector is and is constantly updating that value at that back. And of course you didn't have to use the back insert iterator. You could have just said v.pushback, okay, but this is the way in which you can do this with iterators. Note that v.pushback is a vector-specific implementation, whereas the back insert iterator here is a generic iterator. Yes, it needs to have the type of what it's inserting over handed into it, okay? But it's just much more generic than just say v.pushback. Okay? This code is confusing to understand. I stared at this myself for about half an hour the first time I was looking at this going, what does this mean? Okay? So again, the textbook goes into a lot more detail about what these iterators are doing and what purposes they serve. So we've just spent the last couple of slides looking at input iterators. Let's look at output iterators. And this one I do have some code for. Okay. This here, it's going to go over a collection and use an output stream iterator to output that data in that collection to an output stream. In this case, our output stream is cout, console out, okay? But that doesn't have to be cout. That could be an output stream file, okay? So we have a vector of 5 elements. We use this output stream iterator and then the space to put onto the end of it to then loop using a range-based for loop over our collection and write to the output stream iterator. What do people think this code's going to do? Hopefully it should be reasonably obvious, but it might be a little bit different to what you've seen before. What do people think this code's going to do? So write each element with a space to the screen. Sorry? Yeah, yeah. So hopefully if this works. There you go. So OStream iterator prints 1, 2, 3, 4, 5. Okay, so we had a vector of 1, 2, 3, 4, 5. We created this output stream iterator. The output stream we're going out to is cout with a space appended to it. Dereference the output stream iterator and put the value I into there. And it gets printed out. Again, with printout, that's probably not that helpful because we could just use standard cout and be happy with that. But if this standard cout here was replaced by a file, it would be a very fast way of being able to write data out to a file. Okay? Again, with these slides, go look at the textbook or pick up this code and go play with it yourself. Okay, it's the best way of understanding it. So within C++, there's over 100 generic algorithms available. Okay, so there's a link there to the list of all of them. Okay, they're defined in the header file algorithm, so hash include algorithm. So we've already seen standard sort. Okay, we saw it on Monday. We mentioned it very briefly today. There's a thing called standard sort. Okay, it sorts the container. For copy, okay, there's some code for standard copy. That's how the code looks. You don't have to write that code yourself. It's already in that header file for hash include algorithm. What you can see in this code at this point is, back on Monday we mentioned templates. Here is a piece of template code. Okay, the template says it takes in an input iterator, it takes in an output iterator, two different types. Okay, so copy has an input iterator and an output iterator. The function copy, okay, which returns an output iterator, takes in the beginning, the end location of the input, and an output iterator to where it's going to copy that data into. While first is not equal to last, so while our input iterator is not equal to the last location over what we're trying to copy, dereference what we need to copy into and copy that value. Once you've done that, return the output iterator. Okay? You don't strictly have to understand how that code's working, but that's what the code would look like, or a variant on that code would look like inside for hash include algorithm.h for standard copy. Okay? So for lots of things, you don't need to go write your own versions of these. This is the whole reason why the standard template library exists. You've got a whole lot of standard containers, a whole lot of standard iterators for how you can use them, and a whole ton of algorithms for what you can do with them. Okay? With particular containers, though, they sometimes define their own particular operations, okay? And these can be preferred over the standard template algorithm operators, okay? So I've mentioned list a few times, okay? So, and I said that a list cannot be sorted using standard sort, okay? Because it doesn't have a random access iterator, okay? But list has its own .sort function, okay? And again, you can look these up in the documentation in the tables, okay? So list.sort sorts using the less than operator or a given comparison operation. So you can define your own operation, your own way of sorting, pass that into list.sort, and it will work. Again, we'll cover how to do this in the next 2 weeks, okay? But what you've seen over this week has been all these containers, all these algorithms, all these iterators. That's basically a really quick rush through of the standard template library. Okay, now we've got all that in the back of our heads. A couple of things can happen. 1, you guys should all be able to go and complete assignment 1. 2, now the rest of the course should hopefully make more sense, because the rest of the course we're going to be building on these things and looking at how we could build our own additions to the standard template library, and how we can build code that interacts with it. Okay, and particularly assignment 3, that's going to be the big one. Assignment 3, we're going to be building a templated graph class that standard iterators and standard algorithms should be able to operate on. Okay? So there is some criticisms, though, of the STL. Okay? Cryptic error messages. Unfortunately, you're going to have to get used to when you have a very small bug in your code, 200 lines of error messages. Okay? It's actually kind of quite annoying. That's how the compiler works, though. What the compiler does, if you make a simple mistake, rather than saying, oops, you got a mistake here, it prints out every single possible thing that you could have been trying to do instead. Okay? Best advice for dealing with that is scroll all the way to the top and find what the first error message is. It will help you out a lot. Careless use of STL templates can lead to code bloat. So with the templates, what they do is they get compiled into a particular function every single time you use them. Okay? So if you're using lots and lots and lots of different templates, you can end up with a lot of compiled code that you're not aware of. STL containers are not intended to be used as a base class. Okay, so if you're coming from Java, Java has objects and everything is built on top of objects. Everything extends and inherits from other objects. Okay, so you get things like an array list, and an array list is extending a list, and so on and so forth. That's not how the STL algorithm, so our STL library is built. STL library does not use inheritance or objects at all. Okay, so if you try to extend, for argument's sake, a list or something like that, you're going to have problems. Because the destructors are not virtual, okay? Don't worry about what virtual means at this point, but just basically do not go and extend an STL template or STL library. And also using invalid iterators is a common source of errors, okay? So an iterators hit for end, hit for last position, and you're trying to dereference it. Very common way of getting bugs, okay? So you need to have good testing there. Okay, so that wraps us up for this week. There's a whole lot of stuff in the textbook. Okay, so basically in the last 2 weeks we've gone through half the textbook. This has been the crash course in C++ up until this point. Okay, this is supposedly for easy stuff. From next week we're looking at how to build your own classes. Week after we're looking at how to build operator overloads, and then we look at templated classes and iterators and stuff in the weeks following that. Okay, I'll see you guys on Monday.